Hello, hello.
Hello, hello. Hello.
Hello everyone. Dr. Peter Schultz is the co-inventor of the fiber optics now used worldwide for telecommunications. Dr. Schultz is a graduate of Rutgers University and the MIT Sloan School Senior Executive Program. He is an expert in fiber optic technology including telecommunication fibers and deployment, as well as specialty fibers for sensors. Dr. Schultz, an internationally recognized scientist, holds 26 patents, has written over 22 research papers, and has received numerous awards recognizing his achievements. Since 1991, he has been a member of the National Academy of Engineering. He was inducted into the National Inventors Hall of Fame and has received the National Medal of Technology from President Clinton for his accomplishments. Please put your hands together for Dr. Peter Schultz.
Thank you very much. As the title here shows, my talk will go over the history of fiber optics, how we made the first inventions, what the impact of that has been on society, and then what is going to happen in the future. What are the future trends? It really all started here with this gentleman named Ted Mayman, who actually made the very first laser. It was a ruby laser, and he demonstrated it in 1960. When that pure source of light was identified and shown to be able to be made, it was immediately attractive for communications because it had high frequency, therefore could be modulated at high frequencies and carry a lot of information. But the problem was, how do you use a laser beam for communications? A few years later, this scientist, Charles Cow, at the Standard Telecommunication Laboratories, proposed using fiber optics for laser communications. He wrote a paper which was published in 1966 in which he said, if you could take fiber optics, and if you could make them pure enough, and if you could make them in the right form, then maybe they could be used for communications. And for that paper, he received a Nobel Prize in 2010. He was not able to actually make such a fiber, but he did stimulate interest in many laboratories around the world to try to develop fibers for communications, glass fibers. Here was the goal. If, in fact, you could make a fiber optic that would be able to transmit the laser beams in the right form, then it could, in fact, easily replace copper wire like this. It was significantly higher bandwidth. It could carry much more information than these copper wires. The key was, how do you make it? There were two critical requirements for these fibers. These glass fibers had to have exceptional optical quality. The goal was less than 20 dBs per kilometer. That means if you had a fiber 1 kilometer long, then at least 1% of the light you put in on one end would come out on the other end. That was about the same as the signal losses that you got in copper wire communications at the time. So they said if you could do it as good as copper wire and have amplifiers along the way, then it would be worthwhile. So a goal of 20 dBs per kilometer. The best optical glasses that were available in the 1966 time frame had losses of greater than 1,000 dBs per kilometer. You understand this is a logarithmic scale. So in fact, the improvement we had to make to get from 1,000 dB to 20 dB was 10 to the 98th. Second requirement was that it had to be a perfect single-mode design geometry. That meant that the core of the fiber had to be about the wavelength of the light that's being transmitted in it. The difference between the refractive index of that core and the cladding glass around it, which kept that signal trapped in the core, was 1%, and there could be no distortions, no particles, no irregularities in the diameter, and so forth. So it was really a very tough goal. Very high optical quality and this perfect single-mode design. In fact, here's what the design had to look like. The core of the fiber was about 10 microns in diameter. The cladding glass around it was about 125 microns in diameter. Together, that was about equal to the diameter of your hair. And then there would be a plastic coating put in around that in order to protect it, so to preserve its strength. So the goal was to make this and make it purer than anything anyone had ever made before. Well, as I said, many laboratories around the world went to work on this problem, and one of them was Corning Glassworks, a laboratory in New York State which specialized in glass materials. And they assigned 3 scientists to work on the project. 2 physicists, Don Keck and Bob Maurer, and the guy over there on the right who had brown hair at the time was me. We were young. We were in our late 20s. We had just gotten our, 2 of us, Keck and I, had just gotten our PhDs and had just joined Corning Laboratories to start work. So I think at that time I was about 26 years old. Well, we went to work on this project, and we worked on it for about 4 years, trying all kinds of methods to improve glass, and finally realized the best thing to do is to try to take a different approach. Instead of trying to purify regular glass, standard commercial glass, let's start in a whole different direction. And we found a process that's called flame hydrolysis. In this process, you had a chemical which was contained inside of a chamber. It was silicon tetrachloride, and bubble oxygen through it and pass the vapor into a flame of hydrogen oxygen. In the flame, silicon tetrachloride reacted and formed silica glass, small particles of pure silica glass, which we called soot. And in fact, these particles, if you put this inside of a furnace and heated this furnace up, the stream of particles coming down could be deposited in a chamber and built up layer by layer to make fused silica glass. And this process was used commercially to make this glass, and it made it in pretty large pieces, as you can see here. So this was a pretty high volume vapor deposition technique. Well, our thought was that that distillation process of silicon tetrachloride being a vapor brought over might purify it enough to give a high quality, optical quality glass. And so we took that approach, and as I said, we worked on it for several years and finally came out with an idea that really worked. And this was it. And it seems kind of simple when you look at it now, but believe me, it wasn't obvious at the time. We had the starting material, silicon tetrachloride. We had a second chamber with titanium tetrachloride in it. The titanium, when added to the silica in glass, could control its refractive index, actually raise the refractive index. Passing those vapors through the torch, we then passed them into a tube, and the tube was the silica glass made by cutting it out of that big ingot that I showed you a moment ago. But by passing the vapor through this tube, some of the particles stuck to the sides of the tube to form a fine layer of this doped silica glass. If you heated that up, that layer would sinter and make a clear glass layer. And then if you took this piece and put it in a high temperature furnace, it could be drawn down into a strand of fiber. The whole would collapse, and this layer would become the core of the fiber, and the glass tube around it was the cladding. So that was the idea, and that's what we finally did. And in fact, after some trials and errors, we actually made a piece of fiber that had an attenuation of 17 dBs per kilometer. So we were better than the goal of 20 dBs per kilometer. Now, at the time we did this work, which is around 1969, there were no personal computers. There were no electronic flow meters. This was the setup for our actual glass making, where we made the very first fibers. We used regular mechanical flow meters. Here was the chamber where we heated up the vapors, passed them into the flame. Here's the flame. Here's the tube of glass. It was on a lathe, which was rotating, and we put a vacuum on this end of the tube and suck some of that soot down into the tube to make the layer of glass. It seems kind of crazy, but it worked. And in fact, the vacuum on the other end was just a plain old vacuum cleaner that we had in our laboratory. And we just hooked it onto the end of the tube, sucked the soot into it, and that's how we made the glass. And it worked, 17 dBs per kilometer. Well, we patented that, of course, to try to protect it, and this is one of the first patents here, and it basically shows the idea of having a layer of glass on the inside of the tube and then drawing it down into a fiber so that you ended up with a core and the cladding around it. Now that was 17 dBs per kilometer. We kept working on that, and we found another version of this process that we could use, and we called it the outside vapor deposition process. And again, there I am with brown hair. We had a lathe and we had a rod here, and instead of putting glass on the inside of a tube, we deposited the glass on the outside of this rod, rotating it back and translating it back and forth, and that was rotating. And so layer by layer, we could deposit that soot. And when we were done, we would take that off of the rod and sinter it in a furnace and then draw it down into fiber. And with this process, we were able to use a dopant. Instead of titania, we used germania. And the germania silica fibers ended up with extremely good attenuations, less than 4 dBs per kilometer. And that was in 1972. And that really was the breakthrough to be able to make low-loss fibers for communications. After that, pilot plant was built, and the glass demand started to improve and increase, and people started testing these fibers in the communication links and showed that they work. And it all really took off after that. So, but this was the really important breakthrough back in 1972. Today, fibers are made using basically those processes, the outside deposition process and the inside deposition process, to make preforms. And a preform would be this rod of glass here, and put into a furnace and drawn down as fiber, and then put coatings on it, UV cured coatings, acrylate coatings, and then wound up on a drum. Well, today, that preform, instead of being that little pencil that you saw in my picture, they're about the size of a telephone pole. And to draw fiber, you need a tower that's about 5 to 6 stories high. And the fiber today is drawn at speeds of about 125 kilometers per hour. And the preforms, you coil up the fiber about 3,000 kilometers of fiber on each one of these preforms. So today, it's a huge mass-produced process, but in fact, it's the same glasses and it's the same compositions that we developed back there in the 1970s. Well, they installed more and more fiber around the world, opened up communication links that were high bandwidth, and then in the 1990s, 3 different technologies converged. The first was, of course, our fiber optic high-capacity communication network, which was all around the globe. It was on terrestrial, and it was undersea, connecting continents, countries around the world. At about that time, the personal computer came out. Okay? It didn't exist before that. And then the next important thing that came out about that time is what I call user-friendly software. Things that allowed anyone to be able to pick up a PC and be able to use it and do things. You didn't have to write code and all of that in order to use a computer. When those 3 things came together, what came out? The internet. Okay? Think about that. It took those 3 technologies to be able to give birth to the internet. And you know what the internet has done ever since then. And that was in the mid to late 1990s. So it was a real revolution. And more fiber was required as more and more demands for bandwidth came out. So there was just this sort of constant cycle as people adapted PCs and they had more applications, more need to send that information around, more fiber was needed. And this just kept going and going. So today, here we are, the internet has impacted all aspects of our lives. In the field of higher education, there are now massive open online courses. Back in 2013, there were 250 of them. I think there are at least 500 now, and more than 2 million people annually registering to take these courses. All doing it on your PC online. In the fields of health services, telemedicine, diagnostics, remote monitoring, consultations, even treatment can be done over these internet communication links. In the field of business operations, telecommuting, work from your home, outsourcing. I don't think I have to tell India about outsourcing and what an impact that's had here on your culture and on your economic situation, all for the reason that you had high-speed communications, you have intelligent, well-trained people, and can work in this area and be able to supply those services all around the world. And today, more and more, there are these cloud backup services. Well, basically, the cloud is nothing but data centers, right? It's where all that information is stored. But there are more and more of them. Every one of us is taking pictures on our phones and things like that, and it's ending up in the cloud where we have it stored. Well, that requires bandwidth. More and more of that's happening. And finally, of course, social networking, Facebook and things like that. And now, not just PCs, but what do we have that's come out in the last few years? Smartphones, right? Tablets, making it even easier. Even my wife can do this. She never worked with a PC. She never wanted to do email. But all of a sudden, with the simplicity of these technologies, she's able to do it as well. And that's what's happened, again, as another revolution around the world. More and more demand for bandwidth, more and more need for these fibers. Smartphones and tablets, and I say it's all in the air. People think, oh, well, it's wireless. Well, it's only wireless for a short distance until it hits the first cell tower. And after that, it has to go through a fiber optic communication line to distribute a rest of the array around the world. Information in and information out. So in 2008, think about this, there were no app stores. By 2013, there were more than 100 million apps per day being downloaded. And last year, almost 2 billion smartphones were sold annually around the world. Every one of those requiring that bandwidth to send information. In fact, mobile traffic is growing by a factor of 16 from 2014 to 2016. Just mobile traffic using these things. So there's tremendous use and there's tremendous demand. So where are things going in the future? Well, first of all, there's a need for higher capacity communications fiber. When we first developed the fiber, we thought, this is it. And in fact, as improvements were made to use those fibers, going to multiple wavelengths to send information simultaneously and so forth, the bandwidth of a fiber communication line was about 10 trillion times higher capacity than a telephone wire back in 1900 when it was first developed. 10 trillion times higher capacity. From the 1900s to the 2010 timeframe, if you track the history of bandwidth on communications, it increases logarithmically every year. Whenever you get more bandwidth out there, there's more demand for it. And it keeps growing and growing and growing. So there is a need for improving these fibers. The problem is we just can't make enough of them. As we look to the future and how much bandwidth is needed, we need more than just the standard fiber that we make today. There is an interesting field of new fiber sensors being developed. And there's also a whole new growing field of using high-power fiber lasers. The fiber itself becomes a laser. So I'm going to touch on each three of these. This is the summary of fiber installed, cabled fiber installed around the world. Starting out back in the 89, 90 time frame when it was really quite small, but it was adequate. And we got into here where we're now getting into the fact that we have PCs and the internet is really starting to grow and take off. And look where we are out here in 2014, more than 2 billion kilometers of fiber have been laid around the world. To put that in perspective, 2 billion kilometers of fiber is the same as 20 round trips to Mars. That's a lot of fiber. But it's still not enough. And the problem is we can't make enough. So we're trying to find ways to, in fact, put more information on these fibers for the future. And there's a couple of approaches that are being taken. One of them, two of them are shown here. You remember the single mode fiber that I showed you before, it had just one core in it. So we're now trying to make fibers that have multiple cores in them, and each of those can transmit information at these kinds of capacities. It's not an easy problem because these have to be perfectly centered and just in the right positions because you need to be able to connect and splice these fibers together. And all of them have to have that low loss. And you can only pack so many in there because if they get too close, then they have crosstalk. But 7 to 10 looks like about the most that can be made. And so there's quite a bit of work going on to do that. Another approach is instead of having one mode of light transmitting the information in a fiber, design the core structure in such a way that you could have multiple modes, controlled amounts. Here's several other mode patterns, all of which could be traveling through that fiber at the same time. So in this case, you'd have 1, 2, 3, 4, 5 different modes, each of those controlled information going down them, each of those going down through a multi-core fiber, and pretty soon now you're getting up to where you might have an increase of something like 100 in capacity of a single fiber. Another approach, which I think is quite exciting, is a whole different design of the fiber itself. Here's a cross-section of what we call air core fibers. In this case, it's glass, it's fused silica, but the core is actually an air hole, and around it is this honeycomb of holes, which is actually the cladding. And because of this design, it will act as a waveguide, and you could pass the light signal down through the center of that, and it will function just like a normal waveguide. However, there are some real benefits of it. One is it has very low latency. Because it's an air core rather than glass, light travels at a much higher speed, okay? The glass itself is going to slow down that light. So you can get very low latency, meaning you can send a signal from one point to another at much higher speeds than through the glass itself. It has the potential also of very low loss because the core is air. There's nothing to absorb the signal. And because of this particular design, it can have also very high bandwidth, up to 1,000 times higher bandwidth than in a normal fiber. But it is not that easy to make. And you can run into problems with crosstalk and things in that fiber. This is a new design, same idea, but by adding these extra holes around the side, you can control the distortion of the signal going down through the center. And today, fibers made like this, the best loss we've seen is around 7 dBs per kilometer. Now, the standard single mode fiber, remember I said it was 4 dBs per kilometer, but in fact, over time, those germania fibers got better and better and better. And today, the germania fiber that is used in communications has a loss of only 0.2 dBs per kilometer. You can go almost 100 kilometers between repeaters. So these fibers have to get down to those losses. In theory, these fibers can have losses of a hundredth of a dB per kilometer, sorry. And so they could actually be better than the silica glass, but they're not there yet. they're still at these losses of about 7 dBs per kilometer. So there's a lot of work here to be done. A lot of laboratories are working on that, but they're trying to use these new ideas to make fibers that would be able to satisfy the demand for this bandwidth in the future. In the area of fiber sensors, there's lots of work going on to develop sensors based on the use of fiber optics. I'm going to just show you one, which I think is particularly interesting. This is a fiber which has multiple cores in it, and each of these represent a core in the fiber. And when the fiber is drawn, it's twisted so that these cores take on this helical pattern. And in addition to that, built into these cores is what's called fiber Bragg gratings. It's a variation in refractive index across the diameter rather than along the length. And this creates a rather interesting effect of interference of light. So if you send light into one of these fibers, it will, in the end, be transmitted out the sides of the fiber. And because they're in different positions, when you twist the fiber, you'll get an interference pattern, and you can actually see the shape of the fiber on a computer screen, projected onto a screen, which is the light traveling through there. And I'm going to show you that in the next slide. If I do this right. Oop. I got it. So here's one of those fibers. You see it down here. And here's the image of that fiber on the screen. So whatever you do to that fiber, in real time, shows up on the screen. So there's interest in fibers like this. It's based on the same principles as I showed you in the last slide, but in fact, it could be used in a lot of medical methods where they need to be able to take a fiber through your body and do certain things, but they need to know exactly where it is. For example, if it was doing brain surgery, if you had a laser on the end of that. So this is the idea. There's interest in these fibers. It's just one example of some of these kind of unique fiber sensors that are being developed around the basic principle of light traveling through them. Okay. I think you get the idea. And now I got to, oh, I need to do it this way. You're right. Sorry. I remember. This is the last thing I wanted to talk to you about, and that was fiber lasers, okay? Back in the late 1980s, a scientist named David Payne demonstrated that if you took the same fibers, those single-mode fibers and multi-mode fibers that we were making, but put a rare earth element into the core of the fiber, you could make it laze. So you could actually turn the fiber into a laser, okay? And this was actually quite important because it allowed us to have a light source on these fibers where you had to have repeaters. Instead of then having an electronic amplifier, you could just splice in a piece of this fiber and it became an optical amplifier. And so you had a very passive network that was very easy to build, and that really helped also revolutionize the use of fibers in communications. But the power that came out of these things was pretty low, but it was okay for communications, about 50 milliwatts. Well, people have worked on that to improve on that, and they've gotten themselves up to where now we can make fiber lasers that have powers in the order of several kilowatts, okay? This is the device. It's really a very simple, small cabinet. It can be mobile, and then the fiber cable is coming out here, and the end of that would be delivering 2 kilowatts of fiber power. That's a lot of power, as you'll see in the next slide. This is an example of using one of these kilowatt fiber lasers. in this world. So we're having new high-capacity fibers, new kinds of fiber sensors, and finally, fiber lasers that are really powerful for industrial applications. So I hope you've enjoyed it. Thank you very much. And now I have to go catch an airplane from Lucknow. I hope.
With this, we conclude the talk by Dr. Peter Schultz. Next, we have a talk by Dr. Harald Rose, and it will be underway in a few minutes. Thank you.
Thank you.
Yeah, I will get the power cord, sir.
We'll get the power.
Where is the laser pointer?
Sir, I'll get it. You just need it.
Yeah. I do not yet have power. Okay. No,
Hello. Hello. Sir. वहाँ से म्यूट कर दो।
no.
ये अभी ऑफ कर दो। वहाँ से म्यूट कर दो। यहाँ से ऑफ करने में
Professor Harald Rose is a celebrated German physicist known for his work in the field of electron microscopy. He has a degree in theoretical electron optics from the Technical University of Darmstadt. Professor Rose has had extensive research experience at the New York State Department of Health, the Enrico Fermi Institute, Cornell, etc. He currently holds a Carl Zeiss funded senior professorship at the University of Ulm. Professor Rose has 105 patents of electro-optical instruments and components. He has been decorated with numerous awards for his work, the most notable being the Wolf Prize, won with Nut Urban and Maximilian Heder in 2011 for the development of aberration-corrected electron microscopy. Put your hands together for Dr. Harald Rose.
So, hello everybody. First I want to thank the organizers for inviting me to give this lecture. And on the other hand, I was thinking what kind of lecture should I bring to you. And so I want to have a lecture. Perhaps it's the mixture of a presentation you present for some officials and a mixture is so basic physics that you may understand the physics behind it. And let's say my talk perhaps will be also a lesson for you because I will convince you and show you that in order to succeed, the way maybe to go may be sometimes very frustrating, but at the end, if you have the endurance, it's worthwhile. And now let's start. You see, it's quite interesting. About 2,400 years ago, the Greek philosopher postulated that all matter is made out of atoms. He also said that he considered birth, life, and death merely as a rearrangement of atoms. And you see, his visionary statement has been proven true. And that's the reason that you see, over all the times, scientists wanted to see atoms because seeing atoms is believing. If you see them, you believe that they exist. And but this, you see, was a hard hard way to go, and I will tell you the reasons why it was so problematic. Now here you see the development of resolution in microscopy. First we started with light microscope, and then when you finally reach its limit given by the wavelength of the light, that's the end. And so the best you could get was about half a micron, or a little bit better, but this was not enough, for example, to see viruses. Biologists always say there must be something, but you see, light is not, the wavelength of light is not short enough in order to see viruses. And then there was the electrons came up, and you see with the electron microscope, first it was a rapid increase and in resolution, and but the resolution you see here, it was 100 kV, and in order to get better resolution, that means smaller and smaller wavelengths, you had to increase the voltage. And by increasing the voltage, you put electrons have more and more energy, and that is, at the end, it's like if you have bullets shooting on pigeons, before you see it, it's completely destroyed. So that was a limit, and therefore the only way was to make better lenses, and so that you can achieve atomic resolution. And that's also quite interesting. You know, Abbe was the founder of the Zeiss company. He was really a very gifted scientist. And at that time, one didn't know anything about electrons. All one knew, a microscope, you use light. And Abbe, you see, he also had a visionary statement. He was convinced, he argued that there may be some things between earth and heaven which we do not know yet, which may solve the problem. And indeed, discovery of the electron was this, because at that time when they discovered the electrons, they thought the electron would be a particle. And then Bush showed that each rotational symmetric magnetic field, like a coil, where you have a current going through it, and this acts like a lens for the electrons. And then Ruska thought, oh, that's great. Then let's build an electron microscope. And then he started to build an electron microscope, and suddenly a guy came to him and said, because he was convinced electrons have no wavelength, so I'm not wavelength limited, then I can get very high, any resolution. But then, you see, some guy came to him and said, yeah, there was recently a guy named de Broglie. He postulated that the electrons also have a wavelength. They behave like a particle and like a wavelength. This dualism, you know all you learn in quantum mechanics. And then Ruska was quite frustrated, but then, when he did the calculations, he found out the wavelength was so short, he didn't have to worry. And and then you see came Schultz. He was a theoretician, and he showed that all electron lenses, the rotation symmetric electron lenses, are very poor. So that means the best you can achieve with these lenses is about 100 times the wavelength. Now, I told you that now the wavelength at about 200 kV is about 20 picometers, or 0.02 angstrom. Now take it times 100, then the best resolution you can achieve is about 2 angstrom. Of course, you can, if you say I make the wavelength smaller, but then I showed you, then the energy becomes higher and higher, and you destroy the object. So the conclusion was you can really sub-angstrom electron microscope operating at voltage below about 300 or 200 kV, you need aberration correction. But now it's a problem. Usually you see I have glasses, and my glasses are round. But that doesn't help. In order to compensate for the aberration of the round lenses, you need some elements which do not have rotational symmetry. But at the end, the B must again be rotational symmetric. And this was really a challenge. And in order to show you how the aberrations are formed, you see here, you have, let's say, here you have an object, the electrons are scattered, and you have now electrons with, there is no electron laser, unfortunately, because electrons are fermions, and they can never be all in the same quantum state. And that's the problem. And now that means you always have a certain energy width. You do not have monochromatic, if you have a monochromatic electron beam, you just have one electron in it. That's okay. And now you see, now to make, let's see if you have now electrons of different energy or different colors, you see, in order to get a perfect image, you must image this point into the image point so that all rays come to the same point. But now the blue electrons, they're a little bit faster than the green ones. So they stay a shorter time within the lens, so they are less deflected and intersect the optic axis, not at this point, but behind it. And the slower electrons just in the opposite way. And instead of a point, you get here a disk, and the size of the disk determines your resolution. And in the same way now, you need, even if you have monochromatic electrons, let's assume, then you need to have, because the electrons have also have a wavelength. So you need a large aperture angle in order to get a sharp point that you are not diffraction limited. Yeah? And now you see all electron lenses, the outer regions focus the rays more strongly than the inner ones. And as a result, you again get here, instead of a point, you get a disk, and depending on which disk is larger, you are either limited by chromatic or by spherical aberration. Now, you see, in 1952, Feynman didn't know about this Schultz theory, or he knew that they were very poor, and he made this statement, and you see, he came to the conclusion, forget it, the electron microscopes are just too poor. And yeah, so Schultz was a student from Sommerfeld, at the institute in Munich. At that time, in the 30s, it was very famous. You see, Sommerfeld never got the Nobel Prize, but I think 3 or 4 of his students got the Nobel Prize. Yeah, for example, Hans Bethe and Heisenberg and Pauli. And so Sommerfeld, at that time, quantum mechanics was the things to do. And Sommerfeld, as a physicist, he said because Shatter wanted to go into electron microscope, and he said, at that time, all you get is nice pictures. But we want to get quantitative information about the object on an atomic scale. If you can do this, that we get numbers, then this would, and that was Shatter's dream. And nowadays, you see, you can really do spectroscopy at a single atom. It's just unbelievable. If you would have, or I would have told somebody 15 years ago that this would be possible, they would have said, oh, this guy, it's wishful thinking. So later in 1947, Shatter found an ingenious way how you can compensate for the aberrations. And by using non-rotation symmetric elements, multiple elements. And for example, the first, how get I rid of it? All right, yeah, okay. So here you see that was an electrostatic system composed of this electrostatic cylinder lens, rotation symmetric lens, and so you see the ray coming in. Here is rotation symmetric. Here it's strongly deformed, and here it goes out again rotation symmetric. And here you have astigmatic images. That means a point of the object is imaged in a line. And then here you can place an octopole, and here one opposite, and then you can compensate for the spherical aberration. So here you have a very strongly inside. You have a very strongly deformed path of rays, but when you come out, it's again the rotation symmetric, and everything is fine. And the first, at that time, and to prove that correction works, at that time, it was not directly possible, because the electron microscopes were not limited by spherical aberration, but by all mechanical instabilities or electrical instabilities. So you got, and now in order to show that you can compensate for the aberrations, you increase the illumination cone, so that all rays, most of the rays went to the outer zones of the lens where the aberration were the strongest. Then your image became worse than it was before, and then when you turned on the corrector, then you got back the same resolution, but with a much higher contrast. And and so then, because this first corrector was not stable, mechanically stable enough. So then another so-called Darmstadt project started, trying to build a corrector at that time for the best microscope. That was the Siemens microscope at that time. And here you see this corrector. It's just a cross-section. Now it's at the Seos company in Heidelberg, and you see here the multipole elements, and here's a magnetic round length, and here you have the object in this plate, and and you see the multipoles. They looked like this kind, and for the chromatic aberration, you have a crossed electric and magnetic quadrupole, and in such a way that for the green electrons, which have the right velocity, the forces just cancel out, and then you see if you plate it here, then for the force there's no deflection force for the green electrons, but for the blue ones, they are more deflected towards the axis, and the red ones less, and then with this element, then you can get a sharp image, which is corrected, compensated for chromatic aberration. And here is the first proof I showed that here you have an image that holds in the carbon foil, and here at that time the energy width of the incident electrons was only, it could not be made smaller than about 2 eV. And here you see this image, and then we added the corrector. It was the correction was turned off, and you see the corrector did not deteriorate the image. And what we did then, we put an alternating current on the vanil, on the anode, and of plus minus 130 eV, and then you see the image was completely blurred. And then we turned on, as I showed you, this corrector, and you see then we could compensate for the chromatic aberration. That was the first proof that indeed you could, with such multiple elements, can compensate for the aberrations of the round lenses. And now comes the end of all the correction experiments. These experiments were not just made in Darmstadt, but also there was a project in Chicago by Albert Crew. And Albert Crew, in order to get money, he was not very careful. He was promising too much, that it put this way. And then he also failed. And then there was a meeting in the United States from all experts. It was organized by DOE and NSF, and the experts came together and find these experts and declared the successful realization of aberration correction as unthinkable, whatever means unthinkable. And you see this statement, it was disastrous for the entire community, not just in the United States, but worldwide, because when we applied for money to go on with our research, it was denied. Because they said in the United States there is the Pope, and if the Pope says it doesn't work or you shouldn't do it, then you will not get any support. And and then the reasons for the failure. There was the resolution was not limited by the aberrations, but by electromagnetic instabilities, and mechanical instabilities. Although it took too much time to align the system. Let's say usually an electron microscope is stable, or you have not to do anything for about 1.5 hours. And this is great. But then you do not have to adjust it. But let's say if you need 3 hours to align it, you can never align it, because after 1.5 hours it's in another state. And the problem then was also to determine the state of alignment. And so fast computers were not available, and which you need. And so you need a lot of funds to solve and tackle these problems. They were technological problems. That, yeah, I showed you correction works, but it didn't help at the time. So you have to somehow to solve these technological problems. And so Schultz's statement that was at the international conference is that resolution is clearly limited by the unavailability of funds. And you see, even in the 1996 by Peter Hawkes and Kasper, they are one of the leaders in electron optics. In their books, they also repeated the same thing. They never thought that it would be possible, and if it would ever possible, then certainly not in a commercial microscope operating in the routine basis. And now comes to the Volkswagen project. You see, I had a new design for a simple design for a corrective which should work reasonably. And so then there was we came together. Harald was a former PhD student of mine. He was in Heidelberg at the European Molecular Biology Laboratory, involved in electron microscopes. And this facility that was outstanding. They had the best machine shop you can think of, and they had a good electronic workshop. So the best available. And therefore, I was convinced that this was a possibility to prove that correction really works. And but we needed somebody who nobody will give us money in order that we produce a nice toy. Nobody wants or needs. There is no need for. And so Urban, he was a head at Jülich of looking at material science, looking at structure, and he was very interested at looking at interface, seeing the atoms and so on. And so he also joined us for so we had a mutual research project. We submitted to the Volkswagen Foundation. The Volkswagen Foundation, fortunately, is an independent, not state independent organization, and this project, and finally it was approved, and it turned out 2 years ago. So they opened their files, and we were informed that there were 9 reviewers for this project, and the vote was 5-4 in favor of the project. So if one of these guys would have said no, we would not have get any money, and I certainly wouldn't be here. Yeah, so, and the history of the... Yeah, and this, you see, it was really successful, and so in 1993, we started in 1992, and so the breakthrough was in July 97. So that we could, in gallium arsenide, at the first time we could increase the resolution by a factor of 2, and then especially near interfaces, where usually it's very, because the atom, distance, they differ the location of the atoms, and then you get huge delocalization effects, and if you change a little bit the focus, then suddenly you get completely different structures, and people were not sure what is the real structure. But with the aberration correction, suddenly delocalization was gone, and you could really see sharp the images. And now only short principle. The corrector was made from two sextuplets and two round lenses. So here, these are the sextuplets. There were actually 12 poles in order that you can turn the three-fold field, this hexapole field. And here you see the arrangement you have here. You have here your round, your operative lens. Then you have here a transfer doublet, and here is the corrector. So now the trick is, here you have one hexapole, and you image this hexapole on the other one. Because the hexapole, the first effect, as I have shown you, the first effect is that you see it deforms the electrons, the beam, it puts a threefold deformation on the beam. And only in second order you get a defocusing effect which you want to use. And the problem was, how can I get rid of this unwanted threefold deformation? And the trick was then the following: if first of all, if you image with one-to-one in the telescopic system, you see if you image this sextupole onto this, and both sextupoles are equal. And then you see here it's negative, this ray, and here it's positive. So if we add them both in first, the first order effects cancel out, but the second order effect, the beneficial one, add up. And in order that you see how it works, here you see the electrons coming, let's say, on the tube, and then you get here the threefold deformation. Then they are focused. Then this threefold deformation is compensated by this hexapole, and now the electrons travel on the mantle of a cone, and the angle of this cone is proportional to the square of the strength of the hexapole. So and now you remember the outer rays of the electron lens were too much deflected towards the axis. At the beginning I showed you. And now you see with these glasses, or put it there, now they just compensate for this, or you can adjust it because they compensate for this effect. And with that, and now you see, let's go back. It doesn't. No, I want to. Huh? Yeah, thank you. And you see this arrangement now. If you buy nowadays from any manufacturer a corrected electron microscope, they're all built up in this way. The same corrector, and my students, they founded their own company, startup company. It's called Zeus, Corrected Electron Optic Systems, and so that you now see here. Here you see that when the microscope was finished, it was sent to Jülich and for material science, and they looked at this. That is one of the first images made with this corrected electron microscope, and here is strontium titanate. Now you see here is the strontium, and this row, yeah, that's strontium. And now here is the titan, and now here in between, which you see weakly, this is German, this is oxygen. Yeah? That was the first time that one could visualize oxygen. Before that, only heavy elements. You see, and in order you can look at it, and at these low voltages, if you would have looked at it at 500 kV. You wouldn't have seen it because it would have been destroyed immediately. So, and then you see, it's quite interesting. After we were successful, suddenly the mood at the DOE changed. Because they said, oh, we must also have such a microscope, but it must be better. Because we had a microscope, our microscope was about 1.2 angstrom. Yeah, and now said, yeah, we want to have a microscope. We want to have the world record, if it makes sense or not. We want to have 0.5 angstroms. Yeah, 0.5 angstrom is just the diameter of a carbon atom, yeah, or the radius of the hydrogen atom. Yeah? So, and you see, the corrector was a new corrector designed by myself. I was at that time in the United States. And now you see here, there's a gold with here. Oh, I run out of power. No, here you see the dislocation, and you see it's an incredible resolution of 0.5 angstrom. In order to prove it, you take here just the Fourier diffract from the Fourier transform, and then you see here the spots, the white spots are out to the 50. So that was a proof. Yeah? And then when this was proved, DOE said fine and paid everything. So we achieved the goal. Yeah, and now I come. Do I have some? I think I have some time. Yeah. Oh yeah. Okay. So and now now we're at Ulm, and we were interested in not looking at objects or in material science, not solid objects, but we were interested looking at low C. That means at objects of low atomic number, for example, like carbonaceous objects, biological objects, and so then if we go to low voltages, then we had to open up our, in order to get atomic resolution, we had to open up our aperture. That means we need even to have better correction. We must, so we must increase the quality of the correction. And we need also a monochromator to have a small energy width, because you see, if you go down with the energy, when your energy width stays the same, then the chromatic aberration increases. And so our corrector, could only, this hexapore corrector can only compensate for spherical aberration. So we always have to make then the energy width of the incident electron smaller and smaller, so that the chromatic aberration still does not limit the resolution. And so now I want, yeah, and now the prospect was the reduction of radiation damage by operating below the threshold. Oh, does somebody?
So just press this button.
This one?
This red one.
Oh yeah, okay, thank you. No? Huh. Ah yeah, okay. Yeah, yeah, it's there. Yeah, thanks. And now I want to show you here. What you see here is graphene. Graphene now, you see, for graphene, the Nobel Prize was given, I think, 2 or 3 years ago. Graphene is just one layer of carbon, or one layer of graphite. So it has a hexagonal structure. And it's a quite fascinating material because it has properties like a metal, because the pi electrons say are not localized. So the pi electrons do not belong to a single atom. You have a band structure, and I come to this. This is very very important. And now you see, if you look at graphene with a certain dose here at 90 kV, 95 kV, and 100 kV. And so the knock-on for displacing an atom is about at 90 kV. And now you see what I want to demonstrate, that this is a very sharp border. Here, if you now increase the dose, and then you see here at 90 kV, nothing happens. But here now you see you produce already defects. And here, at even higher, even only by 10% higher, you start to destroy the object. So you must operate below this knock-on threshold. And although I will show you first. Now let's assume we replace one of these carbon atoms by a nitrogen atom. By a nitrogen atom here, for example. And so then you see here only you get a very small change here in the atomic distance. So that means the electron density changed a little bit. And so far I have told you in an electron microscope you can hope for to see atoms. But you also can see the electron distribution. And I will show you this. That wasn't. Now, here, what you see here on the left-hand side is the graphene, which doped graphene. But here is some dislocation from the very beginning. That has nothing to do with irradiation of the electron. So, but now you have, you see here, and what we have here, we filtered out the periodic structure of the graphene. So then you see only this one. But now if you defocus it a little bit here, suddenly you see here, you see two dark, can you see this dark, a little bit dark spots? If it would be a perfect crystal structure, here you shouldn't see anything because you have filtered out the periodic structure. Now you see here, you can see already there is something, and here, that means here now, filtered out, what you see here, this is where the nitrogen is. And because we have filtered out the periodic structure, you don't see the nitrogen. What you see is here the change in the electron density. And this was really, everybody was excited. It was made in Ulm, not by me. I do not the experiment, by the group of Professor Kaiser and Yannick Meyer. And and now I want to show you the following. Here we have again graphene, and here we have a flake of graphene. A flake, a little bit flake sitting on it. And you see, if you now filter out the periodic structure, then you see here the flake. Can you see it? Okay. Now, oh no, I have to go backwards. What happened? Oh yeah, but I want to. Yeah. Now you can see how. Look at it. You can see now how a buckyball is formed. And a buckyball, you know, it's carbon 60. So what happens? You see, you have the flake, and at the edges, the atoms are only, one neighbor is missing. So the bonding energy is reduced. Now then you start to knock on atoms at the edge. And then as a result, the two, it starts to bulge and to form a buckyball. Oh. Oh my God. Sorry, can you? No, here's a better. Yeah, perhaps I can. Another way to protect, you see, our prime concern is how can we see atomic structure without destroying the object. So somehow we need to have some protection. And here, for an example, you see osmium particles within a carbon tube, nanowall carbon nanotube. And now we looked at it and increased the doses. The doses from at 80 kV, the dose, and you see the certain dose, the carbon nanowall, everything breaks, and the object is destroyed. Now, if you go down to 20 kV, although the resolution is poorer because the wavelength is longer, but still, you see, nothing happens. And now, what is at 40 kV? At 40 kV, you see, it's also, that means the knock-on threshold is somewhere in the range near 40 kV. If you operate it above 40 kV, it will destroy the object. And here I want to show you the cycle of dislocation. You see on the left-hand side, upper left-hand side, you have one missing atom, defect. And then you see at the end, here on the right-hand side, you have the two, you have this dislocation. And down, you have the opposite, it's an annihilation. And now I want to show you here the movies where you repeat over again, where you can see how this dislocation is formed and then vanishes. So you see now that with this microscope, now you can also see dynamic processes on an atomic scale. And now, what can we do in order to see radiation-sensitive objects? Yeah? For example, if you have molybdenum disulfide, and you see on the upper left, that was the initial. I will show it form, and if you increase the radiation, the dose, then you see you destroy the object. Yeah? You see it from the left to the right. So, and now we did the following. So I was amazed that it would be possible. Yeah? As I suggested, if it would be possible to have a two-dimensional object and sandwich it in two layers of graphene. Because the graphene has these pi electrons, and the pi electrons, so in this case, the damage was not caused by knock-on, but it was caused by electronic excitation. Due to inelastic scattering, you remove a binding electron, and then the bond will break, and then you get this damage. But if you have now the graphene, I told you the pi electrons are delocalized, like in the metal. And they look out. So if they come in contact now with this molybdenum sulfide or this, and usually before a bond breaks, it takes about 10 femtoseconds. And if you then deliver another electron within this time, then you heal to prevent that the bond will break. Oh, thank you very much. Then, yeah, great. Then you prevent, and now you see this. I was amazed. We have a PhD student. It's a female. Obviously, they have more patients, and she really. I thought, how can it be to put 2 sheets of graphene? You don't see anything and nothing, and she managed it. And what you can see here now, it's. No, what happens? Okay, I'm almost done. So here now, you see the difference. Yeah, the last two is if we have sandwiched it, you can look at it with a very high dose. It does not. There's no. On the left-hand side, you see the damage. Yeah. On the right-hand side, you see nothing has happened. And this now is a hope for us that we can, by using this technique, that we may be able to look at radiation-sensitive objects. Not all of them probably, but there may be an important class of objects where this method helps, so that we can resolve the atomic structures. For example, if you could look at ribosomes or so, that in a high resolution, that would be really fantastic. Yeah, and now I come to the conclusion. And you see, the history of the development of the electron microscope is a story of seeming fruitless efforts to succeed in a mission impossible. You see, it took 50 years from the first ideas how to correct these aberrations until it was realized. And so its final success provides a lesson by demonstrating that real advancement in science requires new ideas, endurance and devotion, and long-time support. And I think this message should go to all grading agencies, not just in Germany, but I think everywhere. So that you have enough time to do your work instead of writing proposals. So thank you for your attention.
Thank you, sir. With this, we conclude our talks for the auditorium. At 4 p.m. at the outreach, we have the e-speak talks by the entrepreneurs. And at 5 p.m. in front of the media center is the Mintra logo. Thank you.
Stay here
Yeah.
for a while. I'll charger.
Yeah.
And then we'll go to beach.
To-
Visitors also. Oh, yeah.
With this laser pointer.